Hey everybody, and welcome back to Controls Analysis and Design. We're going to go over Routh tables again. So in this problem, we have a Routh table already set up with 7 poles at least here listed. So we know that just from the power of S. Before I get started really on this and addressing this originally zeros row, I want to show you what the denominator, how you can actually get the denominator from this table of the original transfer function, if for some reason your instructor happens to ask you that. So the way you do this is when you're reading directly off the Routh table, the very first value in that row is of the s to the 7th. So this is 1s to the 7th. So I'm going to write that down, 1s to the 7th. Now, in these rows, they skip powers of s in each column as you go. So the best way to really go about writing this equation is to go down, and then back up, and then down, and then back up. Because right here you can see you've got 1s to the 7th, but then down you've got 1s to the 6th. So plus 1s to the 6th, going up, 2s to the 5th, 2s to the 5th, down, plus 2s to the 4th, going back up again, minus 1s to the 3rd, going down, minus 1s to the 2nd, and then minus 2s, minus 2, up, down, just like that. That is your denominator. So if for some reason your instructor is forcing you to recreate the denominator that this Routh table came from, that's how you can really do that, just kind of that up and down. Now, looking at this Routh table just generally and how to interpret it, we need to figure out if the system was stable and where the poles lay in the complex plane here, which I drew right here just real quick. So the fact that this row was originally zeros, they went through the process and worked it out so the Routh table is still there. But since it was originally zeros, you have the poles from S6 all the way to S0. There's a symmetrical, even polynomial of poles that are symmetric around the j omega axis. So if you have one pole in the right-hand plane from a sign change or something, then you must have a pole in a symmetric area on the left-hand plane. Or if you have a pole on the j omega axis, then you have 2 poles on the j omega axis, basically, because in order to maintain symmetry, you'd have to have 2 poles right there. Well, I should be writing this correctly. Poles are denoted as x's. So poles, 2 poles right there. So what we're going to do is looking at this. In order to interpret a Routh table, the only thing you need is to see the signs. So I'm going to go ahead, and you only are concerned about the first column. The rest of it you can ignore. So you're looking at the sign changes of the first column. So you got plus 3, plus 1, plus 7, minus 15, minus 9, minus 21. So right here, we have one sign change. So one sign change, that tells us that there is one pole in the right half plane. So that would be like this pole or something like that. We can't tell where it is. Routh tables don't really give you that information. But we've got one pole in the right hand plane, but since we have this row of zeros and this even polynomial, you have to be symmetric about the j omega axis. So since we have a pole in the right half plane, we have one pole by symmetry, we have one pole, oh my goodness, I can't write, one pole in the left half plane. So, can you guys even see this? Focus is a little out of whack. There you go, that's probably a little better. So one pole in the left half plane due to symmetry, which would be this guy right here. Now, there's no other way to tell if there's any poles. We can't count up the rest of the poles, but there's 7 poles unaccounted for. We just wait a second. So 4 j omega poles. Okay, yes. So one pole in the left half plane, one pole in the right half plane in this even polynomial. But we've got 6 other poles that are unaccounted for. Well, those are all going to have to be on the j omega. So if there's any poles that are left over after you do the left hand and right hand plane, they end up on the j omega. So of 6 poles, 2 were used in the right half plane and the left half plane. So we've got 4 poles on j omega. Now, So that takes care of our even polynomial up to S6. But we're missing a pole still because we're supposed to have 7 poles because we go up to the power of 7. So we've used up 6 here. Well, there's no information up here. There's no sign change or anything. So automatically we can say that there's one more pole in the right half plane because only a sign change creates a pole in excuse me, in the right half plane. So the extra pole is in the left half plane. I think I misstated that a second ago. But since there's no sign changes, this pole is in the left half plane. So one more pole in left half plane. So total, we have 2 poles in the left half plane, 1 pole in the right half plane, which is paired with one of these, and then 4 poles on j omega. And if you were to go a little bit further, since we have a pole in the right half plane, in this side of the plane, then it's going to be unstable. And that's just about all the information you can get from there. So hopefully that helps you a little bit with how Routh tables work. You're just looking at the sign changes. If you have an even polynomial created by a row of zeros, that's the only way you can get it if there's a row of zeros originally. Then you go through, look at the sign changes in here, figure out which are right half and left half poles by symmetry, and then whatever left is on the j omega, and then whatever is left outside of this even polynomial, you do sign changes again to figure out where they belong. In this case there were none, so it was in the left half plane, and you added that on. So this was our final answer. There you go.